Okay, so now that we've explained what are joint distributions, what are conditional distributions, and also what happens when events are not independent and we use the chain rule and Bayes rule, we're going to now look a little bit more into continuous distributions. So we focused a lot on what happens when we have discrete events, when we roll dice, when we take out cards of a card deck, when we toss a coin. Those are all discrete events. Now we're going to be looking a little bit more into continuous distributions. So first of all, a continuous variable, okay, we represent it through a density function, okay, and the density function basically can be represented as an integral, okay. The whole area below the integral between minus infinite and infinite, the whole area equals to 1, which is the same thing as saying that the probability that all the discrete events happen in an experiment is equals to 1, okay. Roll a dice, roll dice, and basically you have 6 different events. The sum of the probabilities that any of these events will happen is 1. So same thing here, okay? The probability that you know any of the things can happen, any of the continuous variables can happen is 1. Obviously, when we talk about probabilities, okay, basically it's going to be an integral over a smaller interval. So the probability that a continuous random variable is going to have a value between, say, minus 2.4 and 6.5 can basically be computed as the integral between those two values for the density function, okay, which is computed as the area below the curve between those two values. So if we have a function, say, like this one, okay, like fx, that has this shape, what's the probability that the x has values, the continuous random variable x has values between a and b, is going to be the area below the curve. So it's going to be basically the blue areas and the yellow areas. So we sum these 3 areas, and that's the value of the integral, right? So that's also the value of the probability that x takes values between a and b. Okay, that's simply the definition of the integral. And the probability that you know x basically takes any value between minus infinite and infinite equals to 1, which is the same thing as saying that the probability that a random variable takes any of the possible discrete values is also equal to 1. There's one really interesting type of continuous distribution, which is the Gaussian distribution. Okay, if you take a look at how Gaussian distributions can be distributed, so values can be spread out more on the left, more on the right. It can be, jumbled up all over the place. But in general, the interesting thing about Gaussian distributions is that the mean, it's going to have always a mean and a variance. And the mean is always going to be representing the location of the bump, okay? And the variance is basically how spread the bump is, okay? This is just a distribution of what's the probability that, for different x values, the different x values are taken by the distribution, okay? And what this is telling you is that, the most frequent distribution in a Gaussian distribution, it's always the mean. And specifically, the example that I'm showing here, the Gaussian distribution, or also called normal distribution, has a mean value of 1.2 and a spread of 1. Okay, these are different Gaussian distributions, okay? The blue one has a mean value of 0, red one has also a mean value of 0, yellow same thing, and the green one has a mean value of -2. You see that the bump always happens at the mean value. The standard deviation, as you can see, is, as we explained here, the standard is the spread of the bump. So as you can see here, the larger the spread, say for example, red line has a spread of 1. So say the spread of the red line is much larger than the blue line because the variance is also larger. The same thing happens with the yellow line. Gaussian distributions are interesting to study basically because they, or normal distributions, because they appear in many data that we capture from nature. So for example, the distribution of heights in people follows a normal distribution. The size of things produced by machines, errors in measurements can follow normal distributions. Blood pressure, marks on a test, okay, the typical, bell-shaped curve that many instructors use to divide grades of the students. So it's a distribution that oftentimes appear in nature, okay, and that's the reason why it's interesting and why it's been studied so much. The formal representation for a Gaussian distribution is what you see there. Okay, so basically what we say is that the density of a point x is proportional to the negative exponentiated half distance to the average, scaled by the standard deviation. Okay, so what you can see here is that, you know, we use the exponential function for the half distance, so it's the distance to the average, to mu, halved and scaled by the standard deviation. Okay, that's what the Gaussian distribution is representing. And then there's another important function which is called the probability density function, the PDF, that describes the likelihood that a random variable takes a given value within a range. So oftentimes for a random variable, for a continuous random variable, we would always want to understand, okay, so what's the probability that that value is going to take values, that variable is going to take values between A and B? What's the probability that height is going to be between 5 and 6 feet? What's the probability that the grades are going to be between 3.5 and 4? Okay, that's what the PDF allows us to compute. When we talk about Gaussian distributions, there are two important rules observed in the data. The first one is Chebyshev's rule, and the second one is the empirical rule. So what Chebyshev's rule says, okay, is that, and this not only applies to Gaussian distributions, is that basically, you know, when we observe different distributions, okay, the proportion of the observations that are within 2 or more standard deviations, okay, is at least 75%. So if you take a look at, you know, what's the number, the proportion of observations that we have within 2 standard deviations, it's going to be 75%. And if we take a look at the proportion of observations that are within 3 standard deviations, it's going to be at least 88.89%. Okay? Here what we are representing on the x-axis are the average values, okay, or the distance with respect to the average values, so 1, 2, 3 standard deviations, and on the y-axis we are representing the frequency. And then we have the empirical rule, okay. Here what we are doing is representing the distribution of, for example, IQ scores, but you could take any other Gaussian distribution out there. You could take the distribution of heights, you could take the distribution of grades, and so on. And so what the empirical rule says is that approximately 68% of the values is going to lie between 1 standard deviation, approximately 95% of the values is going to lie between 2 standard deviations, and approximately 99.7% of the values is going to lie within 3 standard deviations. Okay, those are interesting rules that are observed in nature. Okay, and in the case again of Gaussian distributions, like for example IQ scores or any other example that you could look into, those percentages always take place. And the plot on the right hand side is showing basically what happens at the higher end. Okay, so if you values that are larger than, say, 1 standard deviation away on the positive side are going to be 16% of them. Okay, 2 standard deviations, 2.5, and basically larger than 3 standard deviations on the positive side is a very small percentage. Okay, so that's the percentage of samples that you're going to find with those values. In R, okay, how can we extract, say for example, we want to compute what's the probability that a given continuous distribution or a given continuous variable is going to have values between 2 given values. So we can define the function, okay, and then we can basically integrate. Okay, that's what the PDF, the probability density function, that's what we can do in R. So if you have a variable, we take those values, you can say, let's define a function, x, that's going to be, for example, 3 multiplied by x to 2. And now what we do, I mean, this is a function that we have, and basically we can integrate. So let's integrate on f. The lower value is going to be 0.14, and the upper value is going to be 0.71. And that's basically the result of integrating between these two values, and that's also the probability that this continuous distribution is going to have those values. Alternatively, okay, you can also use, there's a package in R that allows you to do that. It's the dist package, distr. You can load that package with the library command. Again, define the function, okay? And in this case, what you can do is define a continuous distribution, that's going to have values between 0 and 1 with that function, and basically compute what's the probability of that function having those values. You can try that, and you'll get exactly the same value. If we want to define another thing that we can do in R, we've already seen what Gaussians are, okay, the exponential functions and the properties that they have in nature, the empirical rule. We can also work with Gaussian distributions in R. So say, for example, we want to create a set of values and basically define a normal distribution. So to create a sequence of values, we can use the command sec. Basically allows us to create a sequence of values, in this case between x and y, between -4 and 4. And we want to have exactly 1500 different values. So what this does is basically it creates a vector that has 1500 different values between -4 and 4, equally distributed. Okay, so it divides the length of 8 between -4 and 4, it divides it into 1500 different values. And then what we can do is basically use the norm to compute the normal distribution. Okay? So what have we just done? Basically, as I was saying, with the sequence command, we are creating 1500 different points between -4 and 4. Okay? And what we are doing with the norm, it's basically we are creating the normal distribution that has a mean of 0 and a standard deviation of 1 with the values that we have. Okay, so for each x value that we have, the norm is going to return us a y value for the normal curve. Okay, we want to create a normal curve. We want to create a Gaussian distribution with those values. So for each of the x values, it's going to create a y value based on the Gaussian distribution. Recall that the Gaussian distribution is just a long function based on the exponential. Okay, so we exponentiate the distance to the mean, the half distance to the mean, and we scale by the standard deviation. That's the formula. So what the norm is doing is taking the x values, applying that formula, and obtaining the y value. And then we can plot it, and we see that the shape is the typical bell shape, is the typical normal or Gaussian distribution. Sorry. And then we can also basically compute what's the cumulative density function. Okay, the p norm is going to allow us to compute what's the probability that the value of x is going to have at least a given value. Okay, so for example, in this case, let's go back to curving, is that if we have this Gaussian distribution, what p norm is saying is what's the p norm of 1. Okay, so the p norm of 1 says is 0.84. Okay, what this means is that 84% of the values, okay, are going to have an x of 1 or smaller. Okay, so for the distribution that we have, the probability that the x value is going to be 1 or smaller is going to be 84% of the times. Okay, and what this means is that the probability of the value of x being larger is going to be 15%. But basically, we can also compute quantiles here. So we can also understand, okay, what's the x value? It's basically the opposite. So what's the x value that is associated to 95% of the distribution? Or what's the value that is associated to having either 2% or 97% of the distribution? Okay, so it's exactly the opposite. So with p norm, we compute what's the percentage of the samples that we have within a given value, and here what we compute is what's the value that has that percentage of elements. So for example, here we could say, okay, what's the q norm for 0.95? Okay, and basically it's saying it's 1.6. So it's around here, okay? 1.6 is somewhere around here, and it's saying, okay, so 95% of all the samples have values of x of 1.6 or smaller, okay? Okay, you can play around with different quantiles here.